Um, I'm Francesco Nori. I've been working with the ICAP that you see in this fancy slide quite a lot, and nowadays I'm in the ICAP facility department. And today I'd like to talk about physical human-robot interaction in particular, but basically how I arrived to the idea that I think I can now contribute to this topic of research. And in particular, we'll try to give you a description of a European project that I will start coordinating in January, which is about physical human interaction. So just a little bit of motivation. This is very standard and straightforward. Robots were designed to be outside the human workspace and confined within cages and with no people around. But nowadays, the European community has been certifying a number of robots that can really be installed nearby humans. And we finally share with robots the same workspace. But still, I think there is a lot of research to be done in order to give robots the ability to be proficient in interacting with humans. On one side, we need robots able to interact with the environment in a better way, to be able to establish contact in a better way. But this, I think, is just a way to really obtain a robot, to design robots which are able to physically interact with humans, so that are able to establish contact with humans in the right way. And the number of applications, if we solve these issues, are several. And I want just to cite a few because since my approach is a little bit theoretical, in the end, I think I can decline what my research does into different contexts and scenarios. So I sketched up a few there. Physical nurse, physical assistance from a nurse. I think it's very important considering also aging population. Exoskeletons are something that are very popular nowadays, and I think that what they lack right now is the ability to physically interact with humans in the right way. And in general, interaction with humans might be the future for a number of applications that are at the moment are not possible for a number of reasons. As a scientist, I've been always fascinated by how humans interact with the environment. The interaction is never pointwise, as opposed to robots. It's actually distributed on an entire surface, and it's flexible and dynamic and compliant. If you see what happens when you basically run, the interaction with the ground is really complex. As I said, it's compliant, it's not pointwise, it's actually distributed over a surface. The distribution of pressure is very different. When we interact with the environment, we adapt our control action to the specific environment we interact with. In this case, with flexible trees, we adapt our compliance, our way of moving. When we interact with humans, it's even more complex. We need to understand what the other person is willing to do. We need to anticipate what the person is doing. And then we need to adapt our control action to this concern. And I think all of this is the core of my research. It has been so far, and it will be in the future. As a control theorist, I've been always fascinated by how humans are able to control a mechanical system which is very far from what we have in humanoids right now. Humanoids are very fast. They have feedback loops of 1 kilohertz, even more, 4 kilohertz sometimes, which is definitely much faster than what we have in humans. Humans have delays, feedback delays, actuation delays, which could be more than tens of milliseconds. So it's definitely, we could say, 2 orders of magnitude slower than humans, faster than humans. So humanoids are faster, 10 or 100 times faster. As a control theorist, I was fascinated by how can we do these amazing skills without having so fast feedback. If you look at what we learn at the university and what we basically teach to our students, feedback delays are really a problem on control systems. But if you look at the human motor control literature that I've been studying for a long time, and I've been also contributing a little bit, you understand that there are basic principles that humanoid robots do not exploit that are instead exploited by humans. And in particular, I have been reading several times a paper by Sandro Mussaivaldi on adaptive strategies. So on the idea that we continuously adapt our models of the environment, and if we change these models, so if we perturb the dynamical models we are immersed in, we basically change our feed-forward control strategy. And this allows us to be more efficient in dealing with delays and being able to cope with uncertainties. Another important mechanism that was instead presented nicely by Bourdet is that we also change the compliance of our body. And this might be a way that we use on one side to interact with the environment in a proficient way, on the other side to be able to cope with a very unstable dynamics. So also these kind of results are the core of my research interest. And the main topic of my research is exploiting dynamics. There are a number of things that you cannot grasp if you just look at the kinematic of a movement. And I think this is a community which, probably this is trivial for you, but it's not in general for the robotics community. The reason why I think that dynamics are important, I have a video on this. But basically, if we want to be energetic efficient, we need to exploit the passive dynamics of the system we are controlling. And dynamics describe things that otherwise are not visible, like exchanges of forces. In this Newton pendulum, it's impossible to predict that the last ball will move, unless you describe the mass and the forces that these objects are exchanging. The mass is not really relevant, but anyway. And you have very nice properties in dynamics. This is very nice. You see this tough guy is not able to lift this up. But if you just give some momentum to the wheel on the front, what happens is that you have a very interesting property, the conservation of angular momentum. So this skinny guy, is not that skinny, but anyway, is able to do something that the other guy was not doing. But there are other properties that are very, very interesting if you look at the dynamics of objects. On the top left corner, you have the so-called Zabinenkov effect. It's a purely passive object, just a weird distribution of mass, inertia. And what you get is you have this two unstable configuration, and the system is continually switching between the two in absence of gravity. This is on the European Space Agency video. What is interesting from robotic point of view is that if you add inertia wheels inside the robot, you get weird behavior, even more weird behavior. You probably know that cube is able to stand on a single vertex just with inertia wheels. So if you think about humanoid robots with many degrees of freedom, distribution of mass in a very complex way, you can get really weird behavior if you exploit these basic principles. But of course, these principles are not that easy to see in a complex systems like an articulated rigid body system. So in general, I like to think of my research as the trying to understand and to model the interaction between two agents. That's a very broad and general topic of research, and that can be really declined, can be specified in different situations. So on one side you have what I call the self, myself, I want to interact with something. On the other side I have the other, the thing I want to interact with. And in between have the connection, which is the contact between the two agents. This is very, very general, but you can think at the self as the humanoid, the other as the human, and the contact between them could be an object that we want to handle together. But you can think also as an exoskeleton, the human that is wearing the exoskeleton, and the interface between the two. So it's really general, and it can be also the human interacting with the environment. And I will try to give you an example of all these cases in my presentation. A little bit of equations. I like the blackboard, the real blackboard with chalk, so that's the only equation I will give you. The self, for me, is a very specific mechanical system that I try to sketch here. A few details of what are the features of this mechanical system. First of all, is underactuated, and I'm not able to control all the degrees of freedom. This happens for humans, of course, because you only can actuate certain degrees of freedom by establishing contact with the environment. The other important part here, which is not that common, is that the state space of this system is not an Euclidean space. It's actually a Lie group. So the derivatives in this space are a little bit different from the derivative of the position of the system. And the reason is that there is not a global and non-singular representation of the state space, but there is a minimal representation for velocities. That's why I'm not indicating this with Q double dot as you typically see, as we've seen in the other slides, but with V dot, because it's a Lie group, and in Lie groups you don't have the correspondence between the derivative of the position and the velocity. It's a convenient way to represent them, actually. And the reason is that I like to represent this system as a floating system. So I don't want the system to be linked to the ground somehow, but I let it free and decide where to establish the contract with the environment. The other important component is the thing that I want to interact with, and I call it the other. Of course, this is very simple, but what I like to stress is that the other is, again, another mechanical system. We have seen very complex models for these dynamical systems. That was really nice to see. But still, the idea is that the mechanical system is underactuated, has very similar properties, but I don't have a direct access to a number of things. I do not have a direct access to its position, to the state of the system. Especially, I don't have direct access to the torques that this system is applying. So that's really very different from what I can do on myself. And then what is very important is the connection between the two. And again, I want to just give a simple example of this connection, but if you see, this is an algebraic constraint, and the way of interacting with these two agents is by establishing the contact and then exchanging forces. So this, I think, is the core of what I like to do, what the core of my research, trying to understand how I can control this kind of system in a different... That's weird. Let me try to wait a little bit, maybe. I disconnect. Didn't like the equation, probably. But that was the only equation. It's not my fault. Let's try again. Thanks. So the way of interaction is through forces, and those are the ones that we can sense. So that's really captures the kind of systems I'd like to control and to be able to characterize. How I want to do this is very simple. I am control theorist as a background, so control theory is for me a way to guarantee a number of properties: stability in the Lyapunov sense, robustness, and ability to exploit the passive dynamic properties of the system. So everything I've been doing so far is based on the idea that control theory is very important to achieve motor control. But my research is really divided into at least three different subtopics. I've been working on developing a technology to implement my research outcomes. I've been working on software to implement my ideas, and I've been working on basic science to develop new ideas. Starting with the technology, I've been supported by a European project. I cite the two have been almost over, and I will present you the next project that I will coordinate. In terms of technology, I've been developing the ICAV, the humanoid robot you see over there. And I've been contributing to different things. At the beginning, I was mainly concerned about kinematics, so the ability to plan movements in the kinematic space. But very soon, the community switched to the ability to control the dynamics of the system, so the ability to control forces of interaction, and I've been contributing to it. And more recently, the idea of compliance also changed the robot in such a way that we could have some compliant actuators in the system. So since the ICAB is an open source platform, it's changing continuously, and it's really adapting to the need and to the new ideas in the research community. I will be very brief on this. I've been working, as I said, on a kinematic software that is able to real-time do inverse kinematics on the whole body of the robot. In terms of dynamics, I've been working on developing techniques for estimating real-time the forces of interaction and the internal forces, so the torques applied by the robot on the environment, the forces applied on the environment and the torques applied at the motors, and to use them to get active compliance that you see represented here. The very specific feature that allows me to do this inverse dynamic control is the combination of whole body distributed six-axis force torque sensors on one side that are located within the structure of the robot. You see sketched here 4 of them, but we now have 6 of them on the entire structure of the robot, combined with a tactile skin that is covering most of the body of the robot. At present, all the body of the robot is covered with the tactile pressure sensor, 12 bits that gives us the pressure on the body. We have more or less 6,000 taxels, so 6,000 tactile elements that allows us to have a fully description of the interactions. You see here a representation of this capability. So the robot is covered with skin. Whenever it's touched, the corresponding area is lighting up here. You probably don't see, but whenever Andrea here is touching the robot, you will have an arrow that represents exactly the force which is applied on the robot. We also compute not only external forces, but also internal forces, so the joint torques. And by doing active compliance, we can regulate the force of interaction, in this case, zero gravity effect. So we are compensating from gravity and letting the robot flow as if he has virtually a very small mass. In terms of software, we have been working a lot also with the other department in the IIT. I've been working on software for modeling articulated body systems, simulate articulated body system, and also interface them with different software. Will be very brief. In terms of software, we developed a simulator on Gazebo, which allows you to simulate different robots. Another important piece of software we developed is the one that allows us to estimate the external forces on the body of the robot. And what is very important for us is to interface this software with a number of different softwares, in particular MATLAB and Simulink that you see represented here. Just to give you an idea what we have been doing, here you see recent results on inverse dynamics control of posture, simulated and on the real robot. This, on the left-hand side, you can simulate yourself. You go to the website and you follow the instructions, and you should be able to run this very simple demo on your PC. The other one, you need an iCab, which is sort of expensive, 250,000 euros, so it's not that easy. But you have one here, so you can see these demos in these days, because there is a version of the iCab here in Toulouse today, because there is a review meeting of a CoRobot project next week. In terms of science, I'll be, again, very brief, but my research interest is guided by control, and I've been working on modeling articulated systems, on controlling articulated system and estimating articulated systems. In the history of my research, in the past, I've been working on dealing with rigid contacts, so the idea of having an articulated system interacting with the rigid environment. So going back to the equations, which is the same as before, but a very simple one, I'm considering only the robot interacting with a rigid environment, and that's a very simple case that nowadays we can solve. And you see the results are represented here. I will have a video. Also this one, probably can start. Let me see. No? Oh, yeah. So the idea is to have hierarchical control. You first are interested in controlling the external wrenches, so the contact wrenches, in order to stabilize the desired momentum of the robot. The redundancy of this task can be used to control the posture of the robot, and finally the activation redundancy is used to minimize and stabilize the desired internal configuration. And you see, if you start moving, if you start doing fast movement, you start seeing the exploitation a little bit of the basic dynamic rules, like the conservation of momentum in this very simple example. This just to show you that now we have like very fast and dynamic movements. So we'll see again the very same video, but this is kind of fast, in my opinion. I bet that I'm not able to do this, so I can try, but I will fall down. And this is fully torque controlled. So you will see that when the robot stops, Daniele on the background will push him, and the fact that the robot is able to detect whole body distributed contact forces allows him to maintain balance by including in the control action the effects of the forces that Daniele is applying on him. The way the equilibrium is maintained is by simply deciding what is the interaction force and then using this interaction force to control the centroidal dynamics of the robot. So in practice, the position of the center of mass plus the orientation of the whole structure. You see that there is a nice compensation when the foot is bring forward, the upper torso is brought backward in order to maintain balance. What I think is really necessary is to start thinking about transition of contacts. So you see here it's the very same slide as before, but I have a small t here, which represents the fact that in everyday life, even during walking, we change the ways we interact with the environment continuously and in a discrete way. And robots are very bad at doing this. There's no really good theoretical framework for understanding how to move from one specific set of contacts to another discrete set of contacts in a smooth way without seeing the change of contacts as a disturbance to the system. That's very important. And this is a very preliminary result, but we have been working on hybrid systems, like in this case the robot is trying to push against the walls, so there is a transition of contacts. And defining what is the desired motion in this situation and what is the reference error for a PID controller is something that I don't know how to do, so we designed our own strategy. So you see here there is desired motion in green and the real motion on the real robot, and the error is progressively brought to zero, like if it was a PID control. But since it's a hybrid situation, it's a switching contact situation, this kind of control is not, I would say, is not something that has been explored enough in the humanoid community, but also it's very new in the control community. So we're trying to bring results in control into the control of humanoid robots. Again, talking about contacts, we have been recently working on this on the real robot. So you will see now that Gabriele will push the robot, and the robot will take a step in the right direction in order to maintain balance. This is very preliminary, but gives you the idea that we need to work more on this, because that's very unnatural, in my opinion, the way it's taking the step. So at present, I'm thinking about moving from rigid contacts to more dynamic contacts. So in this case, you see, for example, contacting with a soft environment, not a rigid one, or interacting with an object that has its own dynamics. So again, the same equation as before, but slightly different. In this case, you have that the things I'm interacting with has its own dynamic properties, but doesn't have any wheel itself, doesn't have any internal torques. And this makes it easier, and that we can apply several techniques. And actually, we did it a little bit. So I'm running out of time. I will not enter into the details of this. But you see here the robot, again, fully torque controlled, inverse dynamic approaches, and in this case, interacting with a seesaw thing. That it's quite an unstable task. Indeed, you see it's not really perfect the way it's interacting with the seesaw. We are still working on it. But I think we need to start thinking about how to deal with this kind of system and how to choose the torques of the robot, so the actuation variables, in order to maintain a stable configuration on a seesaw. Humans can do this very easily, by the way, but you can imagine. What about the future? I want to move towards the most complicated situations, so interacting with humans. So if I go back to the, I go back to the original system that I wanted to describe. The very difficulties about controlling this kind of systems is that they have their own intention. And of course, intention is a big buzzword. But you can understand this buzzword by saying that they're applying their own muscle activation, and this will change the interaction. No matter what, the two mechanical systems interacting will change each other by selecting their control actions. And this is very, very complicated from a control point of view. Before I've shown you that we have been working on things that do not have any internal will, any internal torques. So you can model everything and try to control these systems, but in this case, this is very complicated in my opinion. Why is it complicated? Well, because as I said, if we want to interact, we need prediction. We need to be able to predict a little bit, not too much, maybe 200, 300 milliseconds. But we need to know what the other partner will be doing. And this is, I think, very, very difficult nowadays with robots. What do we need for doing prediction? Oops. This was not intended. I don't like simulation. Sorry for that. Oops. Yeah. Let me do this because I didn't want to put simulations on. Okay. Sorry, I didn't want to have animations. But to have prediction, you need models. I took the example of the solar system. If we want to be able to model the orbits of planets, we need to predict the position of planets, we need to have models of where how the planets move in the solar system. But to get these models, we need observations of the planets. This is trivial, of course, for a research community like we are, but maybe is often not being explored that much, especially in certain problems. But to do observation, we need new technologies sometimes. And that's what basically I'm trying to do now in the context that I was describing. So if you go back to the videos that I've been showing you before, the robot can deal with external perturbances, can sense forces when applied to his own body, but the robot is not aware of what the person is doing, is not aware of the posture of the person, is not aware about the forces that the person is applying in his own structure. And this is very bad from the interaction point of view, because as I was saying before, these are two mechanical systems that are interacting. Is a nonsense to think that we can interact without knowing what the other person is doing or what is the configuration of the other person. So what I think is needed is, in this context, a technology that provides us a way to real-time monitor the position of the person, but also the inverse dynamics of the person. So I've been working on developing a suit that allows us to real-time monitor forces and position of the person to use this information in the control system of the robot. And this idea has been, will be funded for the next 4 years in a European project that is called ANDI. It stands for Advancing Anticipatory Behaviors in Dyadic Human-Robot Collaboration. And the idea is the one you sketched here. So you see the robot, you see a human wearing prosthesis here in particular. But the human is wearing a suit that allows the robot and the prosthesis here to know what the rest of the interacting system is doing. As a first step to have reactive behaviors at first. So I've been working a little bit on a technology that you see here to monitor humans while they interact with the robot. At present, we are working on estimating the system, so estimating the dynamic parameters of the system and real-time estimating the torques at joints of the person. More in general, within the project, we are thinking about being able to build models of the interaction and trying to anticipate a little bit maybe, as I said, 200-300 milliseconds, what will be next. With application, as I was saying at the beginning, in exoskeleton control, I'm done. With exoskeleton control and physical human-robot interaction, as you see here. Yep, that's it. I just want to thank my lab. You see here a little bit of the experiment that we're running. I want to thank my lab, and that's it. If you have questions, I'll be happy to answer. I mean, I had a counter here that says that 30 minutes are passed, but that's okay. If there are questions, I'll be happy to answer questions. Ah, okay. I didn't know. But I'll be happy to answer. Yep.
The results you present are very, very impressive in terms of the quality of the control of the dynamic of the system. But I was thinking why there is no, why you didn't invest on walking. Then this is the limitation of ICUB. This is because you shown a lot of very impressive dynamical motion and nothing about walking. Yeah. Why?
So I like to take this by citing the research done by Raybert at MIT and then later on at Boston Dynamics. He started with OP machines because he had in mind an idea. And if you see the recent videos of Boston Dynamics, so the humanoid walking around, I think the basic control principle behind those machines are really the same that were in the OP machine. But it took 20 years to actually get a walking machine out of the hopping machine. I think I'm paving the way, a new way to do walking. I really believe that when we walk with on very challenging scenarios, like when we walk on soft terrain, unstable terrain, we exploit the dynamics of the interaction. So I started first by trying to understand how to deal with interaction. And then I will progressively go through walking, but in my own way, not in the way that nowadays people are doing it, but bringing the same ideas into the walking behaviors.
But are you suggesting that it will take 20 years to...
If you publish paper, yes. I need to publish paper as well, not only doing... Well, Raybert did it without publishing paper. Yeah. So I'm optimistic in this sense. As Amos says, I'm optimistic because it will take a while.
Okay.
Thank you very much. This is very impressive.
Thank you.
I wonder, in the interactions of robots, your equations are symmetrical for humans and robots. And while robots are controlled by torque motors, humans are not. And I wonder whether you plan to try to implement there the fact that human muscles are not force generators and not torque generators, but work on a different principle. So as a result, so part of the problems with feedback delays that you mentioned may be dealt with by no delay compliance of the so-called motors that adapt to the environment without any time delay. So I wonder whether you plan to have the two equations in principle different.
Okay. Thanks for the question. It allows me to say a lot of things that I'd like to say and I removed from the presentation. First of all, why is it symmetric? I've been working a lot with a group in my former department, which was called Robotics, Brain, Cognitive Sciences, where we had the idea of studying humans together with robots. In that department, there was a nice idea, in my opinion, which started from the idea of mirror neurons. So the idea is that whenever we interact, we have if we have that the interaction is better if we share a little bit of the motor repertoire of the person I'm interacting with. So this is a little bit in this style to just give the idea that it might be good to have the very same embodiment.
And in the right side of the equations, the torques on the right side of the equations.
Yes. Yes.
Nervous.
Yep. Okay, that's the first part of the answer. So the mirror neurons idea is behind the idea of having a symmetric kind of thing here. For the other part, I need a slide. Let me see if I have it on my spare slides at the end. No, maybe it's here. Oh, yep. Yep. I've been working a lot with in motor control when I was in the other department. Nowadays it's a little bit less, but still the ideas are in my mind about how to represent movements, and I've been working on motor control. And I've been looking in particular at the passive dynamic properties of muscles as a way to achieve properties that are not currently available in robots. And I came up with a prototype of it's actually a patent as well, of an actuator that replicates the equilibrium point hypothesis by creating an agonist-antagonist structure. And on top of that, the ability to co-contract in a way that you stiffen up the structure. I really think that it's really promising in terms of control. I called the properties of this system a passive noise rejection, with the idea that with this actuator is able to reject disturbances without resorting to feedback delays. So it's sort of the idea of muscles that I was describing before. So this is still in my mind. I think for certain very dynamic movements, it will be very efficient to have these kind of actuators, also because they are compliant and variably compliant. So I really believe that they are fundamental to create dynamic behaviors. At the moment, the technology is not ready. We need to invest a little bit more, maybe 2 iterations of this. But it's definitely very, very important. And I think looking at motor control theories and how we can describe the passive dynamic properties of muscles and the musculoskeletal structure will be very beneficial for the next generation of robots.
I was just wondering, you said, Bessie, that the prediction horizon of a few hundred milliseconds is sufficient. If you think about interactions between 2 people, I could imagine that there's even for individuals, there's often much longer prediction horizons in human behavior. If you're planning to investigate this as well for this interaction with robots.
Yeah, I was trying to be maybe realistic within the scope of the project. So, so it will be 4 years. Right now we anticipate probably minus 10 milliseconds. We're not anticipating alone at all. We are delayed by 10 milliseconds in perceiving things. So I think that it's very optimistic to think about 200-300 milliseconds. Maybe in certain actions like walking could be much easier because it's repetitive, cyclic, and has a number of nice properties. It could. I mean, I don't know. I don't know how much we need. That's for sure. That's a good question. Maybe I'm not even the right person to ask because I'm a control theorist. I'll be very happy with 20, 30 milliseconds. So, but yeah, of course, it's something to be decided and to be investigated.
Yes, in terms of basic science, I think those problems are very intriguing, very interesting. I have 2 remarks. The first one is that if you want to maybe to address this interaction, you not only have to address how a human moves, but to include how a human interacts in your model. And the second one is, okay, you try to get a model in the machine which is anticipating with something which is itself maybe anticipating. Mm-hmm. And wow, this is really curious stuff.
I agree. It has to do with the fact that my own action as a self can influence the reaction. So that's definitely very, very complicated, I have to say. But humans do it. So starting maybe by doing the measurements on human-human interaction, we could think about how this happens, the idea of leader, follower, these kind of things. And there is literature. I was presenting here today only what I want to do, but a lot of people have been doing a lot of interesting stuff. I'm not saying I'm the only one considering these problems, and this is very, very interesting. Fascinates me a lot. For example, I haven't said that a way to do prediction is to make models, very simple models, but there are a number of models that are available nowadays, like inverse optimal control that was cited by Gentian is a way to do prediction. If you have the cost function, you just plug it in and that's it. You don't need any more. It becomes an autonomous system, no longer an unpredictable system. Or compliance is another way to replace the torques there with something that to replace. Let me see. So if you take this system and you replace tau q with k minus q desired, and you know q desired, that this becomes again a system which doesn't have any internal will. It's just moving with a predefined scheme. So that's something that can be used as a first approximation of intentionality. So there are a number of things that we can already do and sort of go in the direction of understanding and predicting the behavior of a person. But I think it's very fascinating still.
So about the computational time, if you consider the X-sense or motion capture system, the computational time for 155 degrees of freedom is done within 16 milliseconds, including the quadratic programming.
Yeah, time delay is an issue. What we did is involving in the project X-sense on one side and Anybody technology on the other. Anybody technology is doing something similar to what you presented, so a full musculoskeletal model of the human. X-sense is developing the technology for real-time monitoring of humans. So the idea would be to explore possible direction to simplify the models in such a way that we can reduce the computational time to the needs of the controller. So that's something that needs to be explored. And there is a trade-off between accuracy and real-timeness. I'm not an expert. I've been working on real-time estimation on humanoids, which is simplified by thanks to techniques like recursive Newton-Euler, articulated body algorithm, to make it really fast in the computation. With humans, is something still to be explored, especially the trade-off between accuracy and computational time. And this is an exercise that we need to do and we will do in the next 4 years. But that's very, very, very important again.
So I think this is partially related to the other questions, especially about long-term prediction. So you are a control theorist, as you said. Do you think that a prediction model which is only based on dynamics and control is fully adequate for prediction of human intention? Don't you think that maybe including in the loop other principles like artificial intelligence and context awareness might be effective?
Of course it does. Right now I'm thinking about very specific applications. As I was saying, exoskeleton is one application. If you think in exoskeleton, if you have a lower limb exoskeleton, you might boil down the possible scenarios into a limited number of scenarios. And then you can think about having something that is able to classify and understand what is the context. And then on top of that, you can run your prediction stuff. that's definitely important. If you scale up on more complex scenarios, then it's definitely important. But I would say as a starting point, I will try to get a classifier that tells me what is the context. So if I'm walking or turning left or turning right or stopping or starting a step, and then on top of that, trying to use my prediction machine, which is tuned to the specific phase of the movement. So I would say that as a starting point, we simplify the context to a finite number, and then we try to identify the context. But that's of course very important. Thanks.